Понятно, да?
Да.
А в третий раз 25 минут прошло занятие, потому что их потом сняли и куда-то повели на какое-то мероприятие внутри лицея.
Ясно.
Так что вот так мы готовимся.
Да. У них уже насыщенная жизнь.
Да, у них уже насыщенная жизнь. Так, ну что, Николай, я думаю, начинайте. Я буду тут следить за перепиской. Вы такой же член программного комитета семинара STEP.
Хорошо. Хорошо.
Всем...
Да, всем здравствуйте. Перейдем на английский сразу. Да. Hello everyone. Okay, so you already started recording, right?
Yes.
Okay, very good. Very good. So hello everyone. Today we have a sort of a bit more informal, I guess, gathering where we just would like to share our impressions and our experience. So myself, Violetta, and Abdelrahman doesn't have his camera on. Now he has. So we have visited a summer school on interactions of proof assistance and mathematics in Regensburg. It was a 2-week summer school. Well, it's technically autumn school, but yeah. Anyway, yeah. Originally, there were more of us who were going to go there. There were 6 students from the university and me and myself, so 7 people overall from Innopolis were going there. But unfortunately, two of the students did not get their visa approved. They got declined their visa. So only 3 of us were able to go there. But yeah, we'll try to share whatever we've learned, and we'll continue having some related meetings here at the university after. So hopefully we'll be able to somewhat spread the information and on all the other good things that we got there. So anyway, today we would like to just take about half an hour each to approximately, maybe less, maybe more, to talk about just a few highlights from the school for each of us, what we've learned, what we've noted there. And yeah, and I think without further ado, we'll just go to the first person, Violetta.
Is it audible if I say that?
Александр, слышно Виолетту? Или все зависли, кроме... Тебя должно быть слышно, на самом деле. Я могу даже тебе показать так.
Я могу тут отключить. Окей.
Но я не понимаю, что-то Александр завис, Аркадий тоже не слышно. Я просто не знаю вообще, кто-то, кроме тех, кто в Иннополисе, вообще нас слышит или нет.
Да, я слышу.
Отлично.
Аркадий.
Отлично, спасибо, Аркадий.
So first of all, I'd like to thank you for announcing the summer school and for having seminars that were aimed to prepare us for the school. It was very helpful.
Ой, куда-то звук ушел.
Don't worry, it is not emergency. It is just 3 people rush to close the door. How many computer scientists are required to close the door? 3.
Okay, yeah. So the summer school, my impressions, was an amazing experience. A lot of fun and a lot of knowledge, deep dive into proof assistance and homotopy type theory. So the school itself was in Regensburg, beautiful city, medieval architecture, and even UNESCO World Heritage. So it was beautiful there. And also, people that were around the lecturers and other students. It was very interesting to talk to them during coffee breaks, on the dinners. We were discussing, you know, things like Young dilemma, what does it mean to be a monoid in a category? What is simplicial sets, like with hands? So yeah, it was so much fun. And okay, the school was the program. It featured several proof systems such as COC by Iberto. Then I'm not mentioning RZK, I think. Then
I will just, I mean, if you don't have slides, I will just share the screen of my personal information and so this is the website of the school. There's a picture. Yeah, but also some. Yeah.
So there was online by John Harrison, Isabel, mainly research, but Isabel by Angeliki Stovar-Iraqi. There was Lean on the second week, and Agda. Agda by Egbert Wiki, and also
Right.
Colin McBride was using Agda for his lecture. It's back into group assistance. And also there were lectures on math, in particular on homotopy type theory, introductory lectures by Paige North, most accessible, I guess. And on the second week, there was a talk about enabling categories by Benedict Lawrence and categorical semantics of type theory by Steve Audi and Tariq Kram. They were related.
Yeah. This one and then this one. Yeah.
So what else was it? Homotopy type theory. This is a very young field, and I appreciate the story, how it appeared, how people came to learn that. So at first there was Martin type theory, like 1970s, dependent type theory with identity type, and people were wondering, like, it was an open question for 20 years if proof of identity are proofs of identity are unique, and it turned out that they're not by showing the model of type theory in which proofs of identity were not unique. It was shown by Thomas Streicher and Michael.
Peter Lumsden, Stryker, and I think also Peter Lumsden, and I think someone else.
Maybe ask questions.
I think so, yeah.
Well,
Martin Hoffman.
Martin Hoffman, yes.
Every time when I hear that identity is not unique, I believe that it is not identity. So how to call it? Identity should be identity.
No, it's rather proves that two things are equal.
So it is not equality exactly. Still, at this point, I would like to be very strict indeed.
Okay.
So, Leibniz axiom, it is called axiom, but doesn't matter, says that something that is identical is indeed unique. It matches same properties always. Or fits or don't fit. So if it is not exactly this identity, it should be somehow in different way.
Well,
So
then the question is, how do you actually specify this Leibniz identity? Because you can formulate it in terms of a system with a weaker equality, because it does involve. So in Leibniz identity, you talk about properties of things as propositions. Then you have to define what a proposition is, right? And that gets you back to, well, what are your foundations of mathematics? Are you talking about sets where equality is built in and is trivial, or are you talking about a different foundation of mathematics where there's no such thing as built-in trivial equality? So, yeah, even this principle, I mean, it's natural to start from there if you also start from sets. But if you don't start from sets, then yeah. It's not as trivial.
In any case, I still do believe that it is misuse, and it would be better to formulate that this equivalence is not identity.
Okay,
so there
here they have functions in homotopy type theory, and functions do preserve paths, and they preserve paths, they preserve identity.
I think what's important here is to say that this equality, there are just different, let's say, modalities on that equality. There is something that's called definitional equality that behaves in the way that you're used to, in the sense that it's either they're equal or not, and that's it, and that's by definition. And then there's separately, or there's a similar notion of judgmental equality that's usually meant to be the same as definitional, but sometimes they can be separated. And then there is a notion of propositional equality and a notion of computational equality, which are weaker notions of equality, which correspond to the ways. So propositional equality means stuff that you can prove in a formal system that are equal, right? And computational is furthermore a restriction of that. It's not only you don't just prove it, but the proof assistant also can figure out it. I mean, like a sufficiently powerful proof assistant can figure this out. So
I do believe that this is philosophical discussion, but nevertheless, thank you very much for exchange opinion exchange. I also have another question, less formal. Violetta started her presentation with not presentation, at the very beginning she said, homotopy type theory is a young research area. Who is young? You or homotopy type theory?
I think homotopy type theory is younger.
Yeah, okay. Okay, that's approximately of your age. Okay.
I think 4 years younger.
4 years younger,
yes.
Okay.
That depends on when you count the start of homotopy type theory.
Let's call the start of homotopy type theory the
2011, something like this.
2004.
2004.
When the
yes, when there was another model with higher groupoid structure.
Okay.
Right. Model. I'm not sure what it is exactly, but I have one sort of idea.
Nevertheless, thank you very much for answering both my questions. Please continue.
So yeah, that model that we built, that was replacing uniqueness of identity hypothesis. It was the groupoid model, and groupoid is a category in which all morphisms are invertible. So here they sort of have a category and objects that correspond to terms, and morphisms between objects that correspond to identities between them. And it's possible to have several morphisms between the same pair of objects. So this shows that there might be different proofs of identity. And then there was another question, whether the proofs of identity are unique. And it took another 10 years to find a model in which they are different. And And then I'm not sure how exactly it gives rise to our proposed structure to learn more of things. And the thing that I appreciate here is that this model was like exactly the same as spaces in homotopy theory, and it was also related to infinity categories, and it was like I see now how it is both accidentally, how they accidentally came to the same thing, and it was not an accident, so I shouldn't have used that word. But the structure was discovered with several ways, which hints that this was universal in some sense. Yes, and because this.
May I interrupt again?
Yes.
Well, again, philosophical question, but I do believe today is not very formal presentation, and so philosophical questions are welcome. I think so. Well, basically, since you mentioned the structure was discovered, still a topic for mathematical and philosophical discussion, whether mathematical structures are discovered or invented.
I've heard that question.
So was this structure, do you believe that the structure was indeed discovered or was invented? Do you understand the difference? So chair was invented. I think so. Because many people don't use chairs. They did not discover them. Now they can.
Well, because this structure was sort of, people came to that with different paths, sort of hints that it was rather discovered.
So you believe that it was discovered because several different people came to the same structure independently. Okay. A good argument should be taken into account, by the way.
I would say that maybe even if, so I also believe that it's rather discovered, but I would assume that some mathematics might be invented, but then like it's probably some part of, you know, reasoning or whatever that is like invented in some sense of the word, but then from there a lot of mathematics follows, and then all of that is discovered. So you can sort of talk about relative discoverable versus inventable thing. So that maybe if you dig deep enough, you find places that are actually invented, but I don't think we have found those yet. We as humanity, I think. So far it feels like we're discovering stuff, but yeah.
Well, I don't think it's completely discovered. Like that story, well, generally all the story about computability. Yeah.
Kader, could you please repeat once again? Because our moderator today is not very polite.
Yeah,
He
apologies.
contrasts to me when I moderate.
Yeah, that's okay. Kind of jumped in without notice or without warning. Yeah, sorry for that. I mean, I think, yeah, lots of math first kind of invented or proposed and then discovered that the properties are discovered. The whole story of the computability, like, yeah, Church invents, proposes this lambda calculus, and then we discovered properties. Then, yeah, basically, what is the theory of the recursive functions, recursive functions, is again invented, proposed as an alternative, and then discovered that they're actually equivalent. Then again, Turing invents these formalisms of Turing machines. Yeah, that these machines proposes as alternative. Then it's discovered that actually, anyway, it's the same thing. Yeah, they all are equivalent. So kind of, yeah, I think mathematicians pretty routinely invent, in that sense, that propose, construct some things, some constructions, some definitions, and so on, and then themselves or other mathematicians gradually discover additional structure, hidden, kind of in this sense, hidden structure of these definitions or theories and stuff like that, connections to other stuff, equivalences, and so on. So I think it's totally mixed up, both invented and discovered. I see no contradiction there.
Yeah.
Thank you. Please continue. I believe that we should continue. It is not a discussion. It is acceptable, but not the main point of our
Okay. Okay. So I written that in the abstract that like lectures by Paige were most accessible to me, and I learned most out of her lectures. So what she like told is the precise definition of homotopy type theory, and it was new to me that this is Marshall-Webb type theory plus univalence axiom plus higher invented types, and I think I'm gonna elaborate on that a little bit. So first, univalence axiom. There are you can come to that by considering what does it mean to be equal for different kinds of types, and for types like booleans, natural numbers, it's sort of there's only one way to define equality there, like true is equal to true and false equals to false. But for functions,
You can define true is equal to false and false is equal to true. There's an equivalence, non-trivial equivalence from Boolean to Boolean, right? So it yields another.
It yields equality of booleans to booleans.
Yeah, which
It's
is not
just
trivial.
types.
Which is not trivial. Which is
Yes.
not identity. Not reflexivity.
Okay, so I'm not an expert. I'm just sharing what I understood.
Sorry.
Well, so it's, when they want to define equality for functions, the obvious idea is to say that functions are equal if they behave in exactly the same way on all possible inputs. This is called the function extensionality principle. And it is not provable in Marshall-Webb theory. So as uniqueness of identity principle, which also arises from considerations of equality of type of terms in identity types. So this principle says that all proofs of identity are same as reflexivity proof.
May I ask a question?
Yes.
Because I demonstrated pieces of these lectures.
Yeah, this is Paige's notes. Yes.
Well, I always wonder, well, if no preliminary prepared lecture notes, I always wonder whether people simply are lazy. It is just my private opinion, never just private opinion. But nevertheless, I do believe that lecture notes, some lecture notes, let me say, in Russian it is called опорный конспект, should be prepared.
Yeah.
So, what is your opinion? It is just opinion. I don't know this guy, I don't know him or her, I don't know, so it is quite common for many mathematicians just to present flow of mind. But nevertheless, your opinion. So,
These lectures were
your presenter was not prepared, in my opinion.
I think she was, and I think because
Was
she,
prepared.
yes.
But these were notes that were prepared. This was not written during the lecture. This was prepared in advance.
Given another lecture. Okay.
Sometimes it helps.
No, this is the style. This is the style of lectures for some lecturers, and I've used a similar style before, and I think it worked well. But yeah, it depends.
So I started with just my opinion. So
Yeah.
in particular, you can reply. Thank you for your opinion.
Yeah, thank you for your opinion.
Let's continue because we don't rush, but we have limited time.
Okay, I think univalence is in another document.
Yes, lecture 2.
Oh, right.
Okay, so the third is the quality of types, and from considerations of quality of types arises the univalence axiom, and it's those three functional extensionality, univalence axiom, and uniqueness of identity proofs are yes, this is what I'm talking about. They do not follow their. We cannot prove or refute them from Marx-Villett's theory, and we can add them to some special versions of type theory, and addition of each of them is justified by the presence of models of type theory, but the interesting thing here is that univalence axiom and uniqueness of identity proofs are not compatible. Yeah. Probably so we'll have to say that explicitly that univalence axiom states that from equivalence of two types, which is like from existence, equivalence is defined roughly as presence of map from one type to another and from another to the first type that are, and the composition should be identity of the homotopy. And this axiom states that from existence of those two functions, and so such properties follows that there exists a path in some other type in which those two types exist within these types.
Yeah, I think there's a typo actually in the lecture, so it's not very useful here. Yeah, I cannot draw anything on my computer, unfortunately, for now. But so yeah, univalence is when equality that is defined in your type theory is equivalent to equivalence in your type theory. So because so basically equality, the identity, is useful because you can just replace one thing with another and you still get an equal thing, even if your equality is actually the weak equality that we talked about before. But equivalence is an even weaker equality because equivalence is not does not say exactly that the things are equal, but provides instead mappings and something else. And the univalence axiom says that, well, those equivalences, and you can always get an equivalence from an equality because you can just take an identity function, right? That doesn't do anything, and then you get the things that are equal. But you can have non-trivial things that are not identity. For example, for Boolean, you can convert Boolean to Boolean, but in a non-trivial way, you can swap true and false places, and you still get a bijection. So
well, what I meant that time was that I cannot say that true is equal to false. Otherwise, it would lose its meaning.
you cannot say. I mean, yeah, you can say many things, but the important thing is that there is non-trivial equivalence of Boolean to Boolean. a bijection from a set of two elements to itself, which is not an identity, right? And univalence says that, well, those things actually we also want we want our weak equality to also incorporate them, basically, to incorporate those things. So if you do that, then you basically get homotopy type theory. I mean, you need to have some interesting types as well, but you can also choose to not do that, and instead say, but then that, and say that you have, uniqueness of identity proofs. So you don't have the higher structure, and these two things, they are not directly related, but they sort of cancel each other out. So if you have both, if you say that two proofs that two things are equal are indistinguishable, then you do not get univalence. And if you get univalence, you do not get uniqueness of identity proofs. Then basically univalence automatically says that your identities are actually weaker than you would otherwise assume. So these are two incompatible things. And in homotopy type theory, they choose univalence because it allows for a richer structure, and you can still recover your uniqueness of identity proofs for some types, just not for all types. So you can find a place within homotopy type theory where uniqueness of identity proofs holds, and you can do all the regular mathematics in there that you're used to. But then you also have sort of a weaker kind of mathematics that is allowed by univalence axiom. So yeah, I think that's the main point. It's just more, so the theory that you get here is just more expressive. You can still fit in at least most of the regular mathematics inside of it, and you can argue technicalities there. But you also get to experience a wider, more topics, more structures that are interesting, that are natively presented in homotopy type theory and are thus easier to talk about. Yeah, I would say that. Do you have a lot more to say?
Yeah, I got something to say, just a little bit.
Okay.
I also learned that this uniqueness of identity principle is called K-axiom. Yes, and also I know that there exists a K-axiom in model logic, and they're not the same.
Yeah, there's axiom.
Yes.
There's axiom K that relates to uniqueness of identity proofs, and there's axiom K that relates to model logics, and those are different axiom Ks. Yeah, same name for different things. Yeah.
There's also K theory, which I also learned exists.
Yeah, K theory exists. Yes. I can add on that topic that I've met some K theorists at the school, and I've learned that it appears that some of the top K theorists are also marathon runners. So we've understood that K in K theory stands for lots of kilometers. Yeah. So anyway. That's it. So we can go to Abdelrahman. Okay.
Okay.
Do you want to share your screen?
No, I don't want to share.
Okay. Do you want me to share anything?
No, not necessary. Should I speak here or is it already?
It's here.
Already on?
Yes.
Okay. So thank you for sharing your opinions. That was very nice. I myself am going to talk a little less math because, well, I didn't understand as much as you did. So let me start, as usual, by talking first about the organization itself. Like, I want to thank you for inviting us and the organizers for organizing this summer school. I really enjoyed the friendly atmosphere over there. It encouraged socializing, collaboration. It was not, like the typical seminar where everyone just attends a lecture and then leaves, but there was actually like long coffee breaks where we could talk and collaborate. It was a really great location. I like the city of Regensburg. I believe I've made some friends there. And I appreciate the opportunity to meet some of the most brilliant people that I've seen. We had first-hand learning experience from many, like, let's say, founding fathers of many of the theories and the tools that were used and that we studied. However, one comment I might have about the organization was that, well, maybe it's more about my expectations, because I expected there to be a little more about from the computer science perspective, but it had much more pure math than I expected. At least maybe that's just my expectation. But you know, the topics were not announced from the beginning.
May I ask a question? Do you mean pure math, mathematics, or do you mean just too much formalized stuff? There is difference. Some people don't consider, would not like to consider this stuff as mathematics at all.
I don't know if I know enough about it to have an opinion on whether it counts as pure math or not.
Just ask Professor Hall. For example,
He's not here.
it is not math. It is just formalized reasoning, formalized theory.
Yeah, we can say that it required a lot of prior knowledge. Like, I had no knowledge of category theory, group theory, homotopy theory. This
So
was prerequisites.
You believe that it is mathematics? Okay.
Category theory is not mathematics?
Well, there are different opinions.
Okay.
In particular, if you ask mathematicians in this university, I believe, well, it will be not in favor of category theory.
Yeah. I mean, category theory is famously known also as abstract nonsense.
Abstract nonsense.
So, yeah, it was mostly abstract nonsense and a little bit of other things, but yeah, mostly abstract nonsense. So it's
it
fine.
would be better to say it's not mathematics, but formalized reasoning.
Yeah, it's mathematics, definitely mathematics. You should adjust your definition of mathematics, obviously, yeah, but I understand the different points of view. Yes.
I see you prefer set theory then.
Okay, please go ahead.
Okay. Well, if we're going to talk about the topics that we studied there, lots of it was new to me. For example, I learned that there are different foundations of mathematics. Previously, in my bachelor's, we only studied set theory as a base of mathematics. I mean, we also studied lambda calculus and Turing machines, but we did not really study them as foundations of mathematics. But there we got to know, like, category theory, group theory, homotopy type theory, or homotopy theory, I mean, as different foundations of math, and each of them provides different insights and interpretations for the different problems. I also thought it was interesting that homotopy type theory in particular attempts to sort of bridge the gap between them, and all of them can be interpreted in terms of homotopy type theory. And one thing that was particularly let's say new to me, or that I found intriguing, is that I believe the synthetic approach to mathematics, if I'm wording it correctly, where, as I understood, instead of breaking a theory down to its principal axioms, like typical math that we learned in school, we start by defining the axioms according to what we think would be useful. At least that's how I understood it there. Please correct me if I'm wrong. So that was a very nice approach and a very new one to me. And that would probably be related to Professor Shilov's discussion about whether math is invented or discovered, right? So sometimes it is discovered, sometimes it is invented. Personally, I think it doesn't really matter whether it's invented or discovered. It's useful, and depending on your epistemology basis, if it's true, who cares? You know, it's true.
It's useful.
Yes, exactly.
Which I think at this university is also debatable.
True and useful are different.
Depends on your epistemological foundation, because some people take useful as the foundation, as the definition of truth.
Okay.
I forgot what it was called.
By the way, sorry.
Yeah, sure.
We run our seminar today in parallel with international conference on formal and analytical philosophy in Moscow. I believe our session is very relevant to this conference. And they made a great mistake not calling us to organize this session. I think so.
Yeah. Additionally, I also found that many of these new foundations of mathematics are actually relevant to computer science and hence also to software engineering. So like I've never seen anything in computer science that's based on, you know, set theory, for example, but seeing programming languages that take inspiration from category theory or homotopy type theory. And yeah, in this case, I think I'm considering RZK a programming language. So yeah, that was also something that I found interesting. And also I found that formalizing is more fun than I thought it would be. Like I thought initially, I know that computer science started as kind of a branch of mathematics, but then they drifted apart. But then this experience brought them a little closer again to me, because okay, now we have mathematical theorems and we're writing them in code, we're formalizing them. And using a proof assistant was a lot of fun, in my opinion. And I found that these proof assistants are not fundamentally that different from programming languages. They just have different goals, sort of like domain-specific languages. And in particular, I got interested in Lean 4 and how it tries to even further bridge the gap between what's traditionally known as a proof assistant and the general purpose programming language. So it's sort of a programming language that has that, you know, both worlds in one. And I definitely plan to learn it on my own and perhaps use it in some of my projects. Who knows? Lean 4, yes, it's a proof assistant developed by a general purpose programming language and proof theorem prover developed by Microsoft.
4 is just the version number. It's called Lean.
But when you Google it, you should add 4, otherwise you will get all agile stuff. And I've seen, I think it's used more often as a proof assistant than a general purpose programming language, at least according to what Janus Limperk in his Taste of Lean lectures said. But I think, like, from what I saw during this lecture, which I enjoyed so much, I think Lean has a lot of potential for, you know, writing robust code that is proven in the code itself. Like, you do not have to prove the theorem separately and then use the programming language where you can make mistakes. It's all in one place together. So I'm definitely interested in that one. And lastly, now maybe speaking as a software engineer, it was interesting to me to see how non-software engineers or mainly mathematicians use tools that, let's say, are more directed or more common among software engineers, like code editors, VS Code, Vim, things like that. So like they use it in a somewhat different way. Like I've never previously seen a developer who uses VS Code hide all of the toolbars and, you know, everything to just focus on the editing. But I've seen that there when some people missed notifications and probably trying to avoid distractions. But you know, it made me think about how we design these tools, and typically we design them for developers. But this, like for the desk proof assistant in particular, we should design it for a different target audience, and we should try to better understand what are their requirements, even if we're using a tool that is more directed to developers. So yeah, like for example, when anything goes wrong with any of my VS Code extensions, my first thought would be to just check the output logs, see what went wrong, maybe try to fix it on my own. But that seems like something not many of these people would try, which means to me as a developer, I need to design, for example, robust error recovering or error reporting mechanisms for RZK, or whenever designing a tool that is not directed towards developers. So that was just another insight for me. And yeah, I think that's all I have to say.
Anyway, not question for you, but nevertheless, or to you, but nevertheless, in some sense motivated by your presentation. Do you know size of and человека года, как по-английски?
Person of the year.
Не, человека года,
Yeah, man years.
Man years.
Or man months.
How many man years required lean development?
Person years.
How many years required, for example, code? Once upon a time, I heard that basically code team, formally speaking, has only one person with full-time salary. All other are just volunteers or part-time people. Lean was developed in Microsoft Research, so it was very professional. How many people? How many man years?
I can Google that.
It is no question for you, but maybe you heard.
I did not hear.
Yeah,
Like, I don't know. Let's see if Google has any information.
I would say it like this. First of all, there aren't many proof assistants. Just period. It's only now that more proof assistants, experimental ones, pop up, and there are two reasons. First of all, it's a very niche thing, so not many people try to do it. Relatively speaking, I mean, if we compare it, for example, with people implementing programming languages, I think many more people implement programming languages than people who implement proof assistants. And so there are much fewer well-developed techniques to get you into that. There are different algorithms that are required to be implemented. I broke this thing. So let me try. Да, Александр, дай вам слово.
Yeah, thanks. I didn't hear the question very well. So was it the question, how long did it take to develop Lean 4?
Lean or Coke, for example.
Just to compare the effort put into developing Coke or Lean, for example, in man hours or in some other metric.
Yeah. Well,
in money.
For one thing, it's definitely less than developing Clang compiler, even without LLVM infrastructure. On the other hand, yeah, that's heavily depends on how you count. Like, okay, Coq started like in 1986 or something about that. So it's about my age. On the other hand, it had many iterations, right? So first it was calculus of inductive constructions, I believe. Then at some point they added co-inductive constructions, co-induction there and principles around that. Then other additions, yeah, like for now they have like 4 meta languages, yeah, whatever. So it's how to say, experienced many developments and redevelopments, so to say. I believe they still regularly break backwards compatibility between versions. Yeah, the similar story is about Lean. Like, nobody saw Lean 1, right? Like, there was something called Lean 1 internally, but nobody outside this group ever saw it in the wild. Yeah, the first thing we saw was Lean 2. Well, anybody saw. I'm not sure I personally saw Lean 2. Probably it was, yeah, second version already, the first thing I saw there. It still was kind of in flux. It partly support homotopy type theory, so some parts of that, partly this, partly that. Okay, then they revamped it and developed Lean 3, which was pretty solid. And yeah, then there was famous formalization effort from Kevin Buzzard and other collaborators, yeah, developing this MathLib, huge mathematical library on top on Lean 3, yeah, with support for classical reasoning. So that was pretty rock solid. Yeah, full-blown proof assistant, really working. Still, at some point, they decided to redesign it, develop another thing. Yeah, Lean4. Again, they were basing their developments on top of all the experience Leo de Moura in particular and the team gained during all the previous years developing first 3 versions of Lean, right? So for Lean4 specifically, this thing, they spent like 2 years, 2, maybe 3 years. And again, that's mainly Leo de Moura, but with help from other people. So basically 2 people over 3 years, something like that. So just 6 person years, right? Not like insane effort. Yeah, if you don't count the previous, how many years, about 10 years or so, when they were figuring out the foundations, foundational and the logic, foundational system that they would be satisfied with for their Lean system, right? Because yeah, Lean2 was kind of a mess. It supported or supposed to support too many things and somewhat conflicting. Then they get rid of some of this stuff for Lean3, then again redesigned for Lean4. So all this development of these kind of incremental, yeah, kind of learning while you're doing a thing. Kind of similar story with Idris language, for example. Again, mainly developed by sole developer Edwin Brady over some number of years. First, they were developing Idris 1. At some point, they decided to redesign the system and again redesign the foundation of the system. Yeah. So how do you count that? I don't know. Yeah, it's hard to say.
Nevertheless, thank you very much for this historical reference. Thank you very much indeed. Definitely, you are better aware than me.
I believe I found an answer to your question. There are 6 people in the team working on Lean from Microsoft side and Microsoft Research. But also, given it's an open source project, they have many contributors, and in total they have 110 contributors, including the 6 from Microsoft.
Thank you, very interesting.
Yeah, well, I see. I saw several of these late release notes, and they have this graph or diagram, basically what is bar chart, yeah, of the number of commits from different people, and like vast majority of commits are from Leo de Moura, and then like trace, yeah, I don't know, like 20 commits from the second person and less from
Maybe
the
some people push commit bombs, you know, just large.
I don't know.
Yeah,
it's still ridiculous how much work Leo
commit.
does. That's kind of insane.
Who knows? These metrics, I don't take them, you know. Yeah, I take them with a grain of salt.
Yeah, sure, it's very coarse-grained metric. Yeah, and I don't want to say that, okay, Leo kind of single-handedly developed everything.
And also, sometimes you need to change just a few lines to fix a lot of things. So there's also a lot of time going into research and understanding how to properly do something, even sometimes a relatively small task. But yeah. Thank you. Okay. Good. Now then, I can conclude today's meeting with a last set of impressions.
This is the last slide. Thank you very much.
No, I mean, like it's the last part, but I have something to talk about. So yeah, I have prepared a few slides. I'm not sure if they're very useful, but we'll see. So yeah, it's the school on interaction between proof assistance and mathematics It was for 2 weeks. It was very nice to be there for 2 weeks. Not every participant and not every lecturer was there for 2 weeks, but most of them were. Overall, I think there were about 50 participants, but I did not count heads, but I think it's about the correct figure. And mostly the participants were master and PhD students, and mostly I think they were either mathematicians, so with mathematics degree or mathematics major, and a few of them were from computer science, but again, leaning towards mathematics or developing stuff for mathematics. Like some people developed, some people were participating in design and implementation of automated theorem provers, for example. Right, and so the school consisted of lectures and also contributed talks by participants. So usually in the evening, we had a separate section that was devoted to people who wanted to talk about something they're working on, that was contributed talks by participants. So the topics in the school, I think, fell mostly into discussing proof assistants like Kotlin, RZK, a little bit of Agda, and there was also a bit about Lisa, which is a set-based proof assistant. So it doesn't rely on type theory, but on set theory. And it's also implemented as a DSL in Scala, which is very interesting design. But it is genuinely interesting.
Lisa.
So, Lisa, yes.
I believe it's an acronym. What does it mean?
Yes, it is an acronym, and it has sets for S. I don't remember anything else.
Now, what I want to tell is that they're from the university where Scala was developed.
Ah, right. Oh, okay, that makes sense. Yes. There was also a lot of mathematics, some just mathematics, some with formalization exercises and stuff. Well, in fact, most of them were with formalization exercises or demonstrations, but not all of them. And mathematics was also very specific in the sense that it was not all the mathematics. It was mostly homotopy type theory and infinity categories, but there was also synthetic algebraic geometry, algebraic type theory, model type theory, algebraic automata theory, which was interesting. Yeah, so there were other things, but we did not have a lot of what should we call it? Applied mathematics.
Mm-hmm.
So the traditional mathematics. I don't know.
Mm-hmm.
What's it called? So yeah, and there was also a very nice. I think it was 2 or 3 lectures by John Harrison, and a good portion of his lectures was about history and development of theorem provers. In particular, he was talking about whole light. He talked about how they came up with or which problems they faced. And
What is his affiliation right now?
Good question. I think Amazon Web Services.
Yeah.
I think that. So it was very interesting to hear that. He was speaking very well, and, very nicely. So I recommend to anyone to just go, and he probably talked about this elsewhere, so you can probably find him talking about this, or at the very least you can check his slides. But I will not focus on that too much. Now, I wanted to sort of highlight 3 things, I think, for me personally from the school. The first one, I think that was the lecture that I think I understood most, or at least it was the lecture for which the combination of how much I understood and how much new stuff I learned was the highest. And I think it was the lecture by Mike Schulman on model type theories. And so model type theories, they exist sort of for they have existed for a while. I've even read some papers on it. I still, at least before this talk, I didn't quite understand why they're interesting. I mean, yeah, you can do that, but why though? So I think what Mike's talk helped me understand is to give some intuition about why we care about model type theories, or why I in particular might be interested in type theory. And so he gave also some demonstration in Agda. In Agda, there's an extension that allows you to, there's called Agda flat that adds the so-called flat modality and crisp types. What's interesting is that he compared at the very beginning. He compared the compilers in programming languages with interpretations of type theory. So, I mean, programming language you can also see as a sort of implementation of a type theory, and then you can compile it to, to run it and execute it. But that's not very. That's one thing that you can do. Of course, you would want to use a programming language because it's easier to use than machine code or something more low level most of the time. Of course, sometimes you still need to do that. So the corresponding picture is for type theory and its interpretations. You can interpret a type theory in give it different interpretations in different toposes, and toposes are a particular kind of categories, and you don't need to know about them. It's just, mathematicians, like pure mathematicians especially, work a lot with category theory. That's their tool, and they identify sort of the place in mathematics and what rules they have in that particular place by specifying a topos. So it's like the specific machine code or specific architecture, but from the point of view of mathematician. That comparison was quite nice. But also specifically, an example that he gave was about doing synthetic topology. So basically, you would like to do topology, but not in a set-based topology, maybe, or a specific, kind of topology. You want to have a synthetic language, so basically a programming language or a formal language for topology, where you would be able to work nicely with things that you work with in topology. And in topology, you work with continuous functions or continuous mappings. And so there is a classical theorem, intermediate value theorem in mathematics, that says that.
That's the topic of the last class for the first year students.
Very good, very good. So for any continuous function and a point C in the and basically a constant line, horizontal line that you can have, there exists a point, intermediate value, at which your function crosses this line. So there's a point where the function is equal, the value of the function is equal to this chosen point C. Makes sense? Everyone knows this theorem, I think. Yes? Mansour? Not completely. Okay, so maybe I don't know if can I just show? Sorry. I can just stop sharing the screen and I can show the whiteboard behind me, I think, because I cannot use the iPad for some reason. I've now confirmed stop sharing. Okay, good. Good. So if you have a function. So function f, I don't know, maybe it looks like something like this, right? And then you know that, again, let me just, yeah. So it's function defined from A to B. Yeah, I just wanted to use the same notation as in Mike's lecture. So we have A and B. So we have a value f of A here, and probably not the best picture.
Very good.
Let me write it like this, and the value of f of b here, right? So then, if the function is continuous, then the theorem says that if you choose any horizontal line at value c here, the graph of your function will cross this at some point x. So there will be x here, right? Makes sense. And so there's it's a classic theorem, and it's also a fun fact about this is that it's not constructive. So you know that it exists, but you don't actually have a construction at that point. So in general, so then this is the picture, and now I can share the screen again. So then in classical mathematics, you say that for any continuous function, there exists blah, blah, blah. But in classical mathematics, you work with all sorts of functions, not necessarily continuous. So you add this adjective continuous here. If you're working in the topology, you would assume that all functions are, all the functions that you're interested in are continuous. So you would like to just drop this continuous thing and not have extra data that you have to, have around in your proofs, having been required to prove things are continuous. You would just want to have this fact in syntactic topology to be true for any function. But unfortunately, right. Unfortunately, unfortunately, this fact could not be true, and we can show that this is not true again by using a picture. Apologize for having to switch between things.
When I said that presentation should be prepared, I did not mean that everything should be only in presentation.
Yeah,
it doesn't contradict to claim that I said.
So the thing is that when we the theorem itself in a syntactic theory, like in type theory, the theorem itself is also a sort of implication, right? If something, then something else. But the implication itself is also a mapping. It's a mapping into basically Boolean, for example, right? And you can also think about that being continuous. Or more specifically here, we are not actually mapping into Boolean, we're mapping into the existence of this x. And so the mapping into x, so if given the data, we find x, even though non-constructively, we expect this to in a synthetic topology, we expect all functions to be continuous, including the theorem itself. So this means that if, remember, continuous means that if we change the input slightly, then the output changes slightly, right? But the inputs to the theorem are the function f and the value c between these two things, right? But now we can see that clearly this theorem cannot be continuous, not in the useful sense anyway. Because, again, we can draw some function, but now we can change this continuous function to be something different. For example, a function that is constant and then goes here, and here it goes down, right? Maybe we can even make it more abrupt, going like this. So now, if you take your A and B, here, this is A, this is B, for example. And then, so here's your f of A, and here's your f of B. But now, you can choose a horizontal line C, for example, that is close here, right? And then if you modify it slightly, your x, this is supposed to be strictly horizontal. Mm-hmm. So that when you change C slightly, you have a sudden jump in x. Mm-hmm. So the theorem itself is not continuous in C. If you change C slightly, the resulting x can change a lot. And also, it's not continuous in f. How do you change the function continuously? Well, one idea would be to just move it up and down the function itself, not the C, but the function itself, and the same effect will happen. So the function is not continuous. The theorem is not continuous. So if you want to work in synthetic topology, it's not enough for you to talk only about continuous functions, unfortunately. So thus, in synthetic topology, you would like by default to have continuous functions, but then you want to have an extra adjective or modality that would tell you that something that you're looking at is not treated continuously, at least. So in particular here, maybe it's not very well visible on the, I think this is a bit counterintuitively, going full screen is not the best here, because I can show this. So here we have these little flat symbols on the typing annotations. And what these flat symbols mean here in particular, it means that we take these parameters, and parameters themselves are can be continuous. Like the function f is still continuous because it's a function from the interval ab to real numbers. And the type of the function doesn't have any annotations. So we expect f to be continuous by default. But we take this whole function and this c as parameters of this theorem with this flat symbol, which indicates that these arguments are treated discretely, which means that we forget about the topological structure on the on this type and on this type. So on the function space here and on the real numbers here. And we only prove this theorem for each f and each c individually, not the continuum of them. Does it make sense? So this is the way that we can modify type theory to take into account these exceptions to the general rule of a synthetic theory, like in synthetic topology. So Mike then goes on to show some formalization of this in Agda, but more technically, if you want to have modalities, it turns out that they usually come in pairs. Like, for example, it's necessary that it's possible that. And here as well, this flat modality for synthetic topology corresponds to basically forgetting the topology of a space. You just get the underlying discrete set. And then there is a dual modality that basically says takes any topological space and says that everything is just topologically next to each other. So makes it so-called indiscrete topology. It's not really that important to know about that detail. It's just that modalities like this, they can be found in model logic, they can be found in synthetic topology, but they're useful. They also have different interpretations. So one is in synthetic topology. So one is in topology, but another one could be in any other theory. Right. Any questions about this? Right.
Thank you very much for very nice explanations about.
It's not due to me, it's due to Mike. Thanks to him, I can now understand a little bit more about modalities. I would also note that there is a very nice paper that I found and I almost read entirely recently. I will just show you some pictures from it. So it talks about modalities in a little bit more generality. There are very nice symbols in there. So yeah, I like this kind of mathematics, not with numbers, and computations. Yeah. Anyway, I highly recommend. This is like a preprint that generalizes on the model type theory that Mike was talking about in his talk. Well, he was also talking about that. But yeah. Anyway. So another highlight for me is Lean. Lean is, of course, a very, very well-developed proof-assistant / programming language. The tutorials were very nice. There were some good motivational examples for things, good questions and responses in the audience. Yeah, we need more math with cats. Yes, indeed. That should be the next Unicode symbol introduced in the next mathematical paper.
У меня на столе в комнате лежит очень популярная книжка «Статистика и котики». Я подарил вам Александр при встрече.
Yeah.
Так.
Very good. And I was in particular interested in syntactic choices that Lin makes because I do not yet quite understand what makes for a good syntax for a proof assistant. For a programming language, it's slightly different. In proof assistants, in particular, we have to deal with chains of equalities, and different proof assistants deal with it in different ways. In Lean, there are several ways that you can deal with it, but one of this is this so-called calc mode. There's also a similar thing in Agda that can be just defined, not built into Agda. There's also tactics mode in Coq that allow you to do that partially. ISAR has the right syntax. Okay, I have to look at ISAR. But so one question for you then, Alexander. Does ISAR allow you to nicely go from x is equal to y to f of x is equal to f of y?
It's not even ISAR, I believe. Well, it's really easy in whole. Well, the only implementation of ISAR language we have is on top of Isabelle whole. Not only whole, but generally Isabelle, yeah, but mostly used with Isabelle whole. So it's on top of higher-order logic. In higher-order logic, you have classical logic and axioms, and thus extensionality and everything. So it goes from this extensional to intentional, from this equality to congruence kind of effortlessly, and I don't know, usually tactics get it automatically.
I will look into that.
That's not an issue at all. Sorry?
Yeah, I will look into ISAR. Thank you for mentioning it. I know that, yes, there's a separate extensional layer, extensional equality, but if you say that it has the right syntax, then I will definitely look into that and see if I can use some of that.
Yeah, well, that was kind of tongue-in-cheek a little bit. The major thing about ISAR, it's very structured. So it's definitely like state-of-the-art still structural proof language of all the major proof assistants. I don't know, across the board. That's best one, hands down. And recent developments in Coq, kind of recent, and this in Lean, they're definitely heavily inspired by ISAR language for structuring stuff, structuring proofs.
I see.
On the other hand, ISAR is kind of, how to say, elaborate, verbose, somewhat verbose as a language. Yeah, that they like these keywords, they put kind of many words to describe this stuff, the structure, the different connections between parts of the proof, stuff like that. And then they have some shortcuts, like words expanded into several words. Still it kind of reads like English, like textbook proofs, though whether you want that many words and I don't know, shortcuts is a matter of taste. Yeah.
Okay.
So the overall the structuring of this stuff, that's top notch. That's definitely state of the art, and you do want to replicate that.
Yeah.
That's for sure. How exactly, kind of what syntax, the terms? Yeah, that's more of an opinion for sure and a taste.
Yeah. So I would just mention briefly that both Lean and Coq, for example, are very tactic-based, tactic-oriented. Lots of proofs are written with tactics. And the problem with tactics, they're very nice to write proofs with. They're absolutely terrible to read proofs with. because it's development of the proof that happens as a conversation with a proof assistant, but then all of the context is basically thrown out in the text of the proof in the end. So visually, you cannot properly understand what's happening. There's a lot of context. So what you need to do is you step through the proof again interactively to understand what's going on in there. And I would like a bit more declarative approach. I at least prefer that.
I believe ISAR exactly solves that problem.
Okay, so
that's one of the problems ISAR solves, and yeah, it integrates this more declarative stuff with tactics kind of seamlessly and perfectly to my taste.
Very good. Okay, thank you again for reference. I will look into that. So then the last thing that I wanted to talk about, I think, is myself, of course. Yes, so I was so my purpose at the school was, of course, to infect people with infinity category theory and formalizations in RZK. Sort of. So we were there with Emily Rio, Jonathan, another of our collaborators did not go to the school, but he was present in spirit and virtually. So a few points of the state before the school. So before the school, RZK was at version 0.54. It's a prototype, but there is some versioning, and there is some versioning because I already had some users starting from March of this year. So starting from March of this year, the versions started to tick because before that I wasn't the only user and I didn't need to any version support. So, but I had only basically 3 users apart from myself, which was Emily, Jonathan, and then later Frederick Backe also joined. Frederick Backe is one of the main contributors to ACTA Unimath, the homotopy type theory formalizations in ACTA. So we have formalized with Emily and Jonathan, we have formalized the infinity categorical Violetta lemma. There is the separate repository for that and a preprint available. And also with students here at the university, we have started formalizing some basic definitions from the homotopy type theory book. So there's a repository for that as well. If you want to learn homotopy type theory and for some reason you choose as your proof assistant RESC, then this is the repository. You can pronounce it RZK, or you can pronounce it RESC. So the name of the proof assistant is after Charles Resk, but one letter is thrown away. People say that I should keep this name because it's easier to Google. It's not a very common combination of letters apparently, so maybe it will stay this way. And so after the school, there were 6 releases during the school, and basically there was 6 releases on each of the 8 working days. So excluding the first day and the last day, because the first day was just the introductions, and the last day I was leaving the Germany. And thanks to Abdelrahman, we had a language server integrated with this code, and there are some diagnostics and hopefully a better user experience for all. We have at least 15 active users who have just contributed to our main formalization library, which is called SHoTT, which is for simplicial homotopy type theory. Simplicial is the flavor that we have to use to get to infinity categories. There's like a list of contributors there to look at. We have started a Zulip server for RZK to just stay in touch and communicate on things. And of course, if anyone is interested, feel free to join to any of these projects and chats. One thing for me is many more people than I expected are actually interested in doing synthetic infinity category theory, or maybe because I don't know, Emily has attracted a lot of people to that place. That's possible. But also the other possibility is that one of the organizers was Dennis Charles Szynski, who is also doing his own kind of infinity category theory, and he has a few students specifically at Regensburg. So that was probably also relevant. But still, I still thought there would be like 5 people at most, but there were much more. And during the discussions in the school, I've realized that there are like a lot of directions of future work, and like people are interested in experimental proof of systems first and foremost, and there are a few things that have to be that people would like to be able to formalize in the near future. Like in RZK itself, probably directed higher inductive types could be added at some points. But then also the modalities that I mentioned, and there's an extension in ACTA, of course, an experimental extension, but it only allows for one flavor of this. But there are, again, many more interesting modalities. And in particular, there are interesting modalities to be used with synthetic infinity categories. So there's a lot of theoretical, but also practical, but also implementation-wise work to be done, because none of these is actually implemented in any of the major proof assistants. So some of this is not implemented because there is no theory yet, type theory developed for it. But other things do not exist because, well, they are very experimental, and people like in Agda or Koch or Lin, well, in Lin people just abandoned homotopy type theory altogether. They just embraced the traditional view of mathematics, so that of course leaves out the room for others to formalize, to enable formalization for this other kind of mathematics that for in the recent years picks up some steam. So that's one direction of work. But then, of course, my proof assistant being very experimental, it lacks a lot of language features. So it doesn't have even type inference at this point. I have like a whole idea of how to make cool type inference, but I haven't implemented it. There are also things that I would like to have, like type classes or a module system even, because now there's a formalization project, but there's no module system still. And of course, since people are actually using this, it would be good to have an IDE support. So both in terms of doing proper output or reporting from the proof assistant itself, but also supporting the user interfaces for that. So what I understood from all of this is that RZK is not just apparently a small, or at least it's not seen as a super small experiment that just shows that, yeah, it's possible to do this. Let's move on to other things. People are expecting these kind of things to develop, maybe RZK itself, or maybe someone else. I mean, at the moment, I guess there aren't many other people developing these things. Yeah, so this is very fresh, and I think it's interesting to be around all of this cutting edge research for mathematics and tooling for this kind of mathematics. So yeah, like I mentioned, there are many parts of RZK could be developed also as separate things, and so contributors to RZK are welcome. If I wasn't subtle enough, sorry. Yeah, this is the last point that I can make. So yeah, many smart, nice people to talk to, many interesting ideas. These 2 weeks were very productive, but also slightly exhaustive. I'm still coughing, yeah, a lot of entries in the backlog for future work for me personally, but also hopefully for some of students who are interested in this. And the last thing is German food was very salty, and I'm happy to be back with normally flavored food. So that's it. That were my impressions. Thank you all for listening, And if you have any questions, feel free to ask.
I have two questions. First, about recently advertised study group in homotopy type theory.
Yes.
How many people?
How many people had?
How good so far?
We had two new. Well, we have Victor joined online and one Kazorin.
Yes.
And we had one other student joined offline. Yeah, I'm not sure if he's scared and will run away, but I mean, probably not. Yeah. And we had also a few students who we, Violetta, Abdelrahman,
Violetta
Antonio,
is not a student.
a future student. Yes. We had a few people, yes, that we were meeting with before the school to prepare for the school. So we had already these meetings, but they were just closed for the group of people who were interested to go to the school, and now we're just opening that up for more people. And we had, I guess, 2 new people join, and yeah, I think it was a start. Yes.
The second question is just about sightseeing. Have you visited the oldest restaurant in Europe?
The oldest restaurant in Europe? No, but we visited Weltenburg. We had a very nice trip there with a local. Huh? Oh yeah, the oldest brewery. So I mean, we technically didn't go to the brewery itself because it was not very interesting, but we went there. I enjoyed the trip. I enjoyed the scenes, like the River Danube, the rock. Yes. So yeah, so it was very fun. I also had an opportunity to go for a run 2 times, so that was good. Yeah, I also lost my voice for a couple of days. Yeah, I tasted different beers. I didn't like any of them. I don't know. Well, I mean, so it was nice there, but yeah, personally, I was there mostly for work. Okay. Okay. By the power given to me, I'm now adjourning this meeting. Thank you all for joining in and listening to us informally talking about our impressions of the school. Hopefully, we have infected you with some ideas or at least got you interested in some of that, and we can discuss some of them later in later iterations. Yeah, and yeah, thank you all. And I think we can stop the recording and yeah.
На самом деле, спасибо. Я скажу пару слов. Я действительно считаю, что люди, которые куда-то съездили, стоит рассказать хотя бы туристические впечатления. Хотя бы. И не обязательно, it is not necessary to say everything was great, people were smart, just share your opinion. It makes sense. No,
Yeah.
No time to read, listen. I like this slogan.
Yeah, I had the opportunity to visit my distant grandmother also, so that was also good.
Where she is?
In Nuremberg. On my way back, I was able to do that, so that's also nice. Yeah. Всем спасибо и до следующего раза. Пока-пока.